I think we are now recording, so I think we're all lined up and ready to go. Good to see everyone who's here today. I can tell a lot of work went into MP2. I had kind of predicted that that would be the case when the semester was getting started, and I looked at how the different labs were structured and where I personally had trouble in putting together labs. Definitely MP2 was by far the most challenging lab to put together, so I'm not surprised. It was also the most amount of debugging. Before we go into these, I was extremely impressed with the effort, with the perseverance, and the desire just to keep drilling down and debugging on things. And you'll probably won't have a job, where you're rasterizing triangles in hardware as your first position, but that ability to debug and think critically and sleep on it and come back the next day and try it again, that's really going to be helpful. And I think that's going to, maybe you already had that, but being able to just further stretch those skills these last couple of weeks, I think um, will be helpful for you and be valuable development. I also think it'd be great, based on what I'm hearing about other classes and this class and everything together, and based on the tenor of the slides, where everyone is happy you got to a certain point, but you're also just very kind of defeated. It seems like I'm all for having a break. If we could schedule in a break this semester in this class, it would have to be a lab break. I think we probably need to keep meeting as a class and meeting our obligations there. I just have to think about how I could best structure that without hurting any of the long-term goals of the class, end of semester goals. But I'm all for that. If there's a way, maybe it's just by pre-extending MP3. If there's a way you can take a week off and still be fine, I'm all for that this semester. I'll think about that a little bit more, because I could see that in the slides that you're about to present here, that this was, yeah, that's one of the downsides as well, right? Um, of realigning with other classes. I just don't want you to feel the way that some of you were feeling on this assignment. It's supposed to be hard. It's supposed to have stress is okay, but not this burnout kind of feeling, because I think we do have half a semester left to go, and we got to gear up again and do it again and do it again, and still learning different things. And so I want you to continue to enjoy the experience. And maybe we were just on the precipice of this no longer being enjoyable, and that's not the point. This is an elective class. You're supposed to learn a lot, stretch your skills like we have been. You're supposed to enjoy it too. And I want us to stay in that place where things are still enjoyable for you. So I open to suggestions. We can post in general about any suggestions for how we can best structure this semester while still meeting our goals of having a project, and also uh, not burning out in the middle of it. So no, we don't need to take the suggestions now, because I think we have a lot of ground to cover today. But we'll just go in the order of our teams. Do not be concerned if we don't get to you today. The goal of the demo was to be available for the demo in class, and I see all the slides that are there. If we don't get to your team, it's okay. You don't lose points or anything. We probably won't pick it up again. Tuesday is going to be an asynchronous class, so we're not going to pick it up again next Thursday if we didn't get to your team. But that's okay. You don't lose points or anything like that, and people can still take a look at your slides. So we are going to start with group one. I'm going to try to keep things relatively timely here and kind of poke you if we need to go a little bit faster. I could tell that if I asked each team to give a 45-minute presentation on this assignment, you would be able to do it. You had enough to talk about, enough debugging things to talk about. We're still going to try to keep it in that 10-minute range. So having said all that, group number one, you are up. But don't all speak up at once. Take your time.
All right.
Okay, feel free.
I can go ahead. Yeah, so our group is myself, Jacob, Matt, and Nathan. You can see all of our little roles on the screen. And as we kind of noted at the bottom, as we got closer and closer to both the initial deadline and then the extended deadline, we ended up meeting very significantly. It's kind of the nice thing about Discord, I think, is that you could just pop on at like 1 a.m. and see 2 of your group members working, and then just join the channel and go at it.
So here's our primitive assembly kind of overview here. So as you can see on top there, on the top right is kind of our basic diagram. So you've got the basic, initially you set that geo points that just wait for vertex 0, right? And then we just added 2 additional states, one for fan and one for strips, right? Since once you've already kind of filled your vertex pipeline, you're just adding one additional point at a time. and then you're re-putting out a new valid triangle and whatnot. On the right there, you can see our test bench for some of those things. We're just testing all the different primitive types to make sure they're being constructed correctly. And then you can also kind of see the waveform that comes out of it. It's kind of hard to read, but I believe that is a triangle and then fan. Right there, you can see at the top is like the state or the prim type that we're doing. And then you can also kind of see the construction there of, if it's a fan, we want to go to the prim fan state or strip and whatnot. And when we're writing out to the next, the setup phase of the rasterizer. So overall, this piece was one of the more simple ones just because it really makes sense of what you're doing. And there wasn't too many moving parts compared to some of the other ones. So I feel like this one was kind of a good way to kind of jump in and get into it and get something working.
And something that if teams discussed it and made progress on, I'm curious for each team for this part specifically. I understand your state machines will look pretty similar. How you generated this N prim signal. So do you recall how your team did a generation of that signal in your design?
Yeah. So if I remember correctly, with GL points and triangles, it's easy because, they're defined length. And so, once you've hit a certain number of items or vertexes, then, you're at the end. The variable length one where you have a fan and a strip that can go on for just about ever. I believe we ended up using the last signal from the axis stream because we realized that as primitives are being sent over, if you're sending like a variable length one, like a fan or a strip, those are all going to be sent generally as one packet. So it'll send the T last signal through that axis stream interface. And so we're just watching for that as well, I believe. So I can talk about the traversal as well then. We're implementing the same traversal just about as everybody else. Although we did make a couple design decisions that, not sure if they necessarily hurt us in the end, but in theory, I believe it should still work. Just like everybody wait for setup, we wait for the first, the triangle and the information from the triangle setup core to, I don't know if Nathan was talking there. All right, yeah, we'll just cut me off whenever, Nathan. But basically, we're waiting for the triangle and the bounding box stuff from the triangle setup core. And then we're obviously moving into the triangle at the very top, right after it's been reordered, so that the first point it sees is the point with the highest Y value. Once we've kind of moved down in the triangle, assuming that we are going to be inside the triangle, we attempt to move right every time first. That was kind of a design decision we made, that every time we pop down, we're always going to go to the right first. It was just something that we felt made it a little bit simpler, so we didn't always have to worry about what direction we're going. We would always we'd always go left as well. As you can see there, we can move right until we go out, then we'd pop, move left, and then keep going that direction. We'd push, move down, and keep going right. Every time afterwards there. That was just a design decision we made. And we felt like it simplified things while, maybe not necessarily always being optimal. We felt that it should, in theory, still work, and that it just made things a little bit simpler in our state diagram.
So here's a picture of the basic rasterizer. So you can see each arrow, each module has 2 arrows at minimum, showing their in inputs and their outputs. So as you can see with primitive assembly, for example, it's getting that vertex in valid, prim type, vertex last from the axis, and then it's giving back out a vertex in ready, so that way it signifies when it's ready. And then you can move that logic throughout. So you see V0, V1, V2, which become triangle in, get moved down to triangle setup. Prim ready and prim out valid are interacting, so that way both are ready to transmit between each other. And then you see here on the left with triangle traversal and triangle test, the fragments being moved between the two, with the fragment test result being moved up to triangle traversal, and then the commands being moved down to triangle test and triangle setup, with triangle setup waiting for the done command. And all these triangle traversal and triangle test, you see they also have the setup in ready and setup in valid signals going to make sure that everything is completely ready for when to do its work.
Hey, can you hear me now?
Yes, sir.
Yes.
Cool. I guess I can take this one, Matt, because you took the other one, if that's okay. For our simulation, our kind of plan for testing was that we created a TCL test bench script for pretty much each component with a couple examples, and we ran them through simulation. And then we brought everything together, and we also wrote a couple different TCL scripts for them. I believe the simulation down there is an example of one of them. And then kind of like another goal with simulation is that we found ourselves drawing out a lot of these examples just to get a visual representation of what we believe should be happening. And then going back down to the waveform and seeing, okay, did we get what we thought was going to happen, what we believed should be happening, comparing it to that.
And I think we all have a different tolerance for how much of this we can do with testing, right? So you do need to do a few of them, I think, for at least the starting triangle. But can you really do all the entire triangle for the red triangle and trace every single traversal and see that you got the right results for each one, or just kind of look for patterns and see that it looks reasonably correct after you check the edge cases for a few triangles? I don't know for each team how you made that determination of when you were pretty happy with simulation and then just move on to testing on the board at that point.
So I think our team in pretty much every single lab this semester has forgotten to do the driver change. Just kind of frustrating because we, spend all the time simulating and we're convinced it works, and then we put it on the board and we get nothing, and then learn that we misread the document and we were missing a driver change. So this time was no different. So we had to, of course, add, the basic driver changes on the bottom in order to properly set the prim type and, actually, copy the prim type onto the board. And then we also added a pulling loop inside of our swap buffers that would pull the status register of the rasterizer. We did fix the color issue because our colors were initially off on the color wheel, and we wanted to kind of shore that up. Unfortunately, for other reasons, we couldn't get the color wheel working, but we did at least verify that the driver fix to clamping colors did in fact fix our color wheel colors.
Gotcha. So now onto this big thing. We had a couple of problems initially with kind of our technology. After class, we just tried to work with Professor Zambrino, and we just had our machine have a black screen when we remote connected to it for, I think we ended up waiting over 5 minutes with him.
I'd like to also note this is the first lab where camera's been in color the entire time.
Yep. So our camera has loved to be in IR mode. And for the last lab, it seemed to shift into color once we put up color and stay there for a while. But for this lab, it was switching back and forth and favoring IR mode, even if there was color on the screen. Thankfully, Zambrino figured out some sort of tweak to keep it in color. It has stayed in color mode, I believe, since. So that's been great. We've also continued to have some problems with old code staying in when we run things. We're still working on it, but I think we've solved it by just kind of like resetting everything and recloning our repo.
I think this screenshot, which I guess you can't see when I'm in front of it, this probably wins the award for probably should have simulated first. For this is the red triangle right here, right?
Yep.
Yeah. That's
so
fine.
I can talk about that. Our problem there is kind of to the left there. Initially, we weren't actually updating our stack when we pushed down. Therefore, when we would push down and then pop left, it would go back to basically the original vertex. And then we updated it. Well, I updated the Y. I didn't actually update the X on the stack. And then we got something like on the right there where it's returning to the origin of the vertex point. And yeah, of course, simulation easily showed that. And this is our results here. With the right triangle there, you can see, we have a little bit of a cut there that would flicker between the top and bottom. And then it would repeatedly draw the random triangles over and over again. And then in our bottom right, I don't believe we ever fixed being able to draw triangles in certain orientations upside down.
Thanks, team. That's great. Yeah, I think that rand triangles test turned out to not be very useful. I mean, it's nice to test and see you're getting triangles, but because of how it layers all the triangles on top of each other, you don't actually know. It doesn't tell you very much, right? It tells you if you're kind of close, but it can basically never tell you if you have it correct. So it's a nice visual, but it doesn't. It's a bit of a stress test that you can't actually pass that stress test just by looking at the result on the screen, unfortunately.
What was interesting about that too, like the flashing version you just saw, that was before we added a pulling loop to our buffer swap. So we were drawing, it looked like most of the triangles, at least, we were drawing correctly. And then once we added in like a pulling statement to wait until we actually finished our rasterization, it basically would only draw like 5, 6, 7, 8 triangles. So I do think like we had some bugs in there that we never would have caught without waiting for that loop.
Yep. And it could also be that part of your traversal doesn't look like it was taking the starting direction into consideration. So you may have actually been doing the whole basically the whole bounding box, which is fine too, but this may be a little slower than it otherwise would be, but that's fine. We want it to get corrected, then we worry about other functionality. My thought was in testing rand triangles, you'd see that teams would see that the first 7 were working, but we fail on 8, and then you'd isolate case 8 and make that a new test case. But I think for a lot of teams, this try paint was probably better for that anyway. Just draw it until it breaks, and then that tells you what you need to know about a test case for breaking. So thank you very much, Team 1. Team 2, you are up.
All right. Well, on the screen, you can see kind of what we each worked on. I worked mostly in the primitive assembly design and then a lot of debugging. Maggie helped out with the triangle traversal, primitive assembly, and we all debugged in primitive assembly. Ryan primarily focused on triangle traversal, and Daniel focused on our triangle setup and was very kind to also help design an OpenGL application for us to test. These are some of the diagrams for primitive assembly. They're very difficult to read on the screen, but very similar to the previous group. We would go back into a wait for vertex state. We actually reused the wait for vertex states rather than making our own states. And then we would end once we captured a T-last. I will point out that T-last did become a little bit of a headache later on, in part due to latching, and we made some wrong not latching, but we made some wrong assumptions as to when T-last would be valid. Ryan can talk about that later, but we can move on to the next slide.
So we just figured y'all can turn your head sideways, but we weren't quite sure what to do for this because it was very similar to the stuff that was in the MP-2 document. So we kind of just put our flowcharts together. And so the top one is our primitive assembly. And then that talks to the triangle setup, which then goes to test and triangle traversal. Christian's triangle traversal is very put together, as you can tell. But yeah, it was just, the basic design that was provided.
All right, I'm going to try to keep this brief because Christian says I ramble. So for general simulation, basically what we did was we would open up TriPaint. We would find a triangle that brokered, basically ended up like a box because it broke traversal. We would grab those points in the ILA. We would put them in a triangle.txt, which is currently being covered up by that screenshot of Discord. Then I would plug it into a tickle file. Or a tickle script. I would copy that into the simulator. I would run it. And then I would also simultaneously put those points into Reed's JavaScript application, which by the way, thank you very much. You are the greatest of all time. And then I would basically, when I would find a triangle that broke our traversal, I would try to look for one that broke pretty early on. So like if the top point and then it was just a straight line all the way to the edge of the screen. And then I would basically step through, figure out what state happened and what state should have happened, and then went back to the traversal code and patched it. And then the draw fans and draw strips was also that Daniel made, was also very, very helpful. Yeah, we could just add points and it was like try paint.
And I just want to add, I know, Reed, you're not going to want to, toot your own horn, but I think you collectively saved a lot of hours these last couple of weeks. You may not realize it because it didn't take you necessarily that much time, and it was partially just for your own, understanding as you built that. But you saved me a lot of time too, by the way. So not just the students in the class, you collectively saved this class a lot of time just by something that was relatively straightforward to do, and I think anyone could have done, but you took the initiative and did it. And really hard to debug this if you don't have good ground truth for what the setup equation should have been. And yeah, I concur with that sentiment.
All right, so we had quite a few bugs, quite a few moths in our computer. So for traversal, so the first thing was I misunderstood the push move down. Like I was checking the direction we needed to go, but I forgot in my head that we'd always be going in the opposite direction from the way in which our line start position currently was once we push move down. So we were going the wrong way and we didn't have anything drawing on the screen. So I fixed that. Second off, were lots and lots of edge cases because I didn't think of them when I was first writing traversal or finishing traversal. The next one, there's a screenshot in the top of the pop move left. This is a bug that probably exists in everybody's code. Essentially what happens is if your line start position X is on the bounding box, we subtract one from that point without ever checking to see like if we are at the bounding box X. So we gradually step farther outside of the bounding box. And I noticed this in simulation because I was checking our current position. I was like, 65,000 is probably not where we're supposed to be. So that resulted in a change in traversal. This was for all the pops. And then also push move in. If you start on the edge of a bounding box with your triangle, it'll subtract or it'll add one and it'll step outside of the bounding box. It also I needed to pass in our bounding box to triangle test. This way, when we were adding or subtracting, I think it was C5 or C6, I don't remember what the C's were, we were actually still checking the correct point. And that needed to determine whether or not we were on the bounding box. However, this failed timing by about 3 nanoseconds, so we just scrapped it. Not 100% sure why, but it didn't save any, or it didn't fix anything functionally, just it would have caused a speed up. Second off, primitive assembly. Essentially, don't trust the ILA because it lies. Our T last signal, we assumed that it would stay high from the moment that we sent, for instance, if our triangle strip had 4 points, and Christian can correct me on this, after we sent the third point, we'd expect that T last would stay high until we sent our fourth point. Is that correct, or am I misremembering?
No, when the fourth point is valid in data stream, T-last would go high. However, that doesn't mean that T-last is valid the cycle after that. Even though the ILA is showing it's high, we can only assume that it would be valid for that one cycle where it is, that data is valid. Basically, that just led to us running fans and strips correctly for some time in steady state, and then randomly that behavior wouldn't be what we assumed, and we suddenly latch onto the wrong points and we'd be out of order. This was very instrumental to us getting what we have of color wheel working.
Yeah, so basically we had the right thing, and then after like 5 or 6 seconds, it would flip flop, so the final point would grab on the first 2 points, and we didn't know what was happening. Triangle setup, we thought that we'd have to scale the colors for some reason, because basically we wanted to get get it to match Reed's calculator. And so Daniel thought we needed to scale the colors, but we didn't. And then also we had assumed C4 was, or we didn't assume that C4 was in Q1.31 format. We were treating it as Q1616, so our colors weren't working. Essentially, everything was a solid color as represented by the screenshot in the middle. And then finally, the computer was doing some funky stuff. At the bottom, you can see a GIF of it just flashing on and off. So sometimes our screen would just flash. Second off, we had lasers, or what Ben Pierre aptly named lasers. And essentially, yeah, I was looking through Traversal trying to figure out what the issue was. Couldn't figure it out. Ends up it was either a bad cable, bad monitor, something like that. Apparently, that could have saved us 3 days of debugging if we had just used SGP FB transmit. However, we did not know about that. But as Zambrino is hovering over it, that is in fact the picture that shows, it's working 100%. And then the bottom white block rectangle, that was one of our edge cases, essentially, with a really thin obtuse triangle. It would just continue on because I wasn't stepping down, or I wasn't doing something correctly. I don't know. That's it for challenges bugs.
Yep. So to wrap things up, these are our results. In the upper right-hand corner, you'll see the 2 OpenGL applications that we made for drawing a fan and drawing a strip. We got some crispy triangles. So we finally got like our red triangle to work. We had it working kind of like early on in the weekend, but we did have some flickering in certain areas that we kind of fixed with, I believe, clearing our cache or flushing our cache. And then we still ended up having some flickering towards the end. As you can see in the color wheel and in some in rand triangles, it would kind of flicker there as well. And then even in Snowflake with that aliasing there. This could be because, well, whenever I was grabbing these screenshots, I didn't have some of the changes in our driver. So we're adding a status register for our render output and then checking or waiting for that status register to go to 0. So that could be the issue there. I haven't got a chance to simulate or test that yet, but this is where we ended up for MP-2.
All right, great team. I especially really like the kind of the one-off test applications. You knew you had trouble with strips, as every team did ultimately, and you made an application that would really just isolate that as a test case. And so I think that probably saved some time. Although the issue with that was a really subtle one, and I don't know if the ILA is lying, right? The ILA is capturing the signals it has going into it. I know what you were saying about that, but I think that issue of whether or not T-last should be staying high or not, that's partially, I would say, a bug in the Vertex fetch core. But in my mind, it should only be high for that transaction. That T-last should signal for this last transaction, this is the last one, whatever you define last to mean. But I did see, as you saw, that it was just staying high. So once you had that latch, that seemed to fix the issue. And I feel bad about every cable that has to be wiggled. That's not the first time. It's the second time now this semester. It was truly a hardware cable issue. I don't really know how that really happens in practice. You have a computer and a setup that's working just fine, and all of a sudden, and no one's there, no one's touching it, no one's moving these machines around, and all of a sudden the cable needs to be unplugged and replugged. But that transmit application, I think, helps for that, right? So that's the real truth of what's in your frame buffer. Everything else is just camera effects or smudges on the screen and things like that. So when in doubt, always just do a quick grab of that. That's for all teams, and you will. I'm not going to answer that question, Parker. Okay, team 3, you are up.
All right. So team 3, Nathan did, as usual, a lot of the work on this project, partially because he just likes to stay up very late or very early, depending on how you look at it. Justin, primitive assembly, some of the frame detection and debugging. I also worked on primitive assembly and made all the diagrams because we're not going to lose points for that this time. And then I also set up GitHub project board so Nathan could just kind of like idea dump into that. And he typed probably more just text about how to implement everything than the actual VHDL and C code or C++ code combined.
At some point,
Um,
you'll have to share that with the class. Is it just
yeah.
pages and pages of Nathan thought process, which is
it's a
good. I mean, I
lot.
love seeing it.
It's a lot, yeah. And then Sava worked on demo applications, and I guess was just a general genius. So yeah, for primitive assembly, I kind of worked on the actual implementation of that, but Nathan came up again with the actual how to do that. Essentially, what we're doing is for some of the states, like if we've got triangles, we'll start way back at the beginning and get 3 points again. With a strip, since really only 2 of the points are changing, we kind of shift points down. Like V1 goes into V0, V2 goes into V1, and then we go back to get the vertex 2 stage and just kind of pass those down. And then for triangle fan, it's also kind of similar, but we're only shifting V2 into V1 and then moving back into the vertex 2 state. And then we also have our end of prim reg, which Nathan can probably explain a little bit more about where that comes from.
Oh, okay. I thought, never mind. You mentioned I could explain it. Go ahead.
Continue on, team. Nathan will get his chance to talk. You can talk a little bit about this
I
diagram.
guess I can.
This
I
is a
can
pretty
take the full
detailed one.
diagram.
Okay.
I guess we didn't have that coordination down. So the basic architecture is essentially the same concepts as the skeleton we were given. There's a variety of small optimizations made to each module, maybe not shown in some of these. But really what happens is the prim type is set. We have a couple versions that worked at different times. Maybe the first working version is just like this, and primitive type is set in a register controlled by AXI. And then we have like a GL points pass through, which essentially is a data flow pass through all the way through our module. Otherwise, the data will go into primitive assembly. I think everyone's familiar with this concepts because they've implemented them very similar, and that gets transacted with setup, which then calculates all the outputs, and then we get into a steady state of traversal and testing. The individual connections, I guess, I can't really describe perfectly, but should I take this slide as well? Just because I got some of the.
Sure, why not?
So for simulation in general, we were quite hesitant to simulate things and make some of these by hand. Primitive assembly was easy to simulate, and that was one of the simulations we were willing to do, and we got that working. Triangle setup, we had a pre-prepared calculation, step through those calculation steps, as well as just verifying every single thing come out the end. But then once we got to traversal, we did like a basic simulation of a few different like in out test results, as well as it running into a bounding box. But we couldn't do it. We didn't want to do any full real triangles with it. So at some point we just started testing on hardware and learned that doing that gets much harder unless you have great interfacing via software, and you can kind of see how your hardware is, which includes the ILA, but the ILA is hard to configure, like to provide a wide variety of input regarding your hardware state. So at some point we used a lot of AXI registers for both controlling and debugging our design. So I kind of listed some of this stuff out. We implemented the status registers a little bit more intricately to have some more status info. For example, we could tell if the rasterizer was working on one overall bigger job, if specifically traversal was occurring, testing was occurring, setup was occurring. Something similar existed for rendering the output. It could tell if it was working on a fragment right now, or if it was still waiting for like a T-last signal, so it's busy in the overall sense. So this kind of stuff helped us detect end of primitives and stuff to properly synchronize with the driver and swap only at the end of the draw. I guess I don't want to go through all of these, but yeah, we have hardware debugging with some error state detection, halting, which can be controlled with the software register. And then I guess.
So Nathan, let me interrupt you briefly, and I think you have a lot of nice hooks that you added there, and a lot of teams would have been a few days ago. We're getting to that point where they realize, well, the AXI stream ILA we have set up only gives us so much information. We really need to introspect and understand what's happening in our state machines. And a couple different approaches we talked about, just I guess over Discord mainly, and using an ILA specifically to debug internal signals has its challenges. It's hard to really connect those signals back to the original signals in your design. Inserting the ILA itself can affect how synthesis happens, and you may wind up in a weird situation where the design works only when the ILA is in place, and then for some reason doesn't work, or misses timing when the ILA is in place, and then makes timing when the ILA is no longer in place. So it impacts the design itself. For what it's worth, this type of approach where you're adding software accessible debug information is a really nice approach. I think it's a very nice way to do it. We do it in a very basic way that I set up for you, which is like a 1-bit status, 1 or 2 bits of control. But adding those registers or refactoring those registers that are there for you, it's giving yourself a software controllable ILA. And you don't have to use the ILA. If you have enough of those registers and you can pull them in software, you're just in a much better testing place than setting up the ILA, doing one test, checking if you're getting the exact bit or not in the right location. Or if you're just doing it blindly where you have no information about what's happening in design, you're just getting pass-fail results. I think the quicker for MP3 teams can get to a place where you don't necessarily have to, go to such extremes necessarily, but for MP3, the hardware design itself is not nearly, I think, as challenging as MP2. It's much less VHDL, but debugging is equally challenging, I think. And there'll be very clear places, I believe. They're not there for you already, but very clear places for teams to add similar kinds of hooks. Where am I in my state machine? That's going to tell you a lot. What are the values of my internal registers in the design? Just pushing those up a level to a status register will allow you to really understand what's happening in your design, and you'll just get it done that much quicker. So I just wanted to add that. I know you didn't want to go into all the details of that.
Yeah.
And in any hardware design, the more introspection from software we can have, just the more pleasant of an experience it is to understand what's happening and why things are or not working as we expect them to be.
And I'll stop myself from rambling about it, but I thought the tagging point was interesting. I didn't mention that. It was on the slide. But we did start generating a system. I think Merkle helped, especially with detecting TLAS to properly detect when everything is busy or done with a whole primitive. There's some special hardware for that, as well as like the ID of the job that it's working on. So basically the driver would generate an ID. So this, in theory, was supposed to help us track multiple draws in a single frame, which we thought would help with color wheel, but we never finished the driver side implementation of draw arrays to correct for offsets. So we haven't actually gotten the triangle to draw for that.
And I'll ask your team and other teams, no one got the full color wheel to work, and that's okay. Is that non-zero offset tricky though, or that should have been a pretty straightforward thing to deal with? So non-zero stride length or non-one stride length, trying to do that with the custom DMA controller and going back to those data sheets, no one was expected to do that. But for not starting at 0, I feel like that would have been pretty straightforward. You're just changing a pointer. That's what I thought it all was going to be.
I thought I'd update the source source pointer in the DMA request. I don't know if I had the right offset, and I only tried a few times. We didn't have as much time to try to get that working before yesterday.
Sure.
The first ones I did clearly weren't grabbing the right points or something because it was drawing a strange like artifact on screen. I don't know if I sent you a screenshot of that or not, but
I might have seen it. I don't recall. All right, well, please continue.
Okay.
Thanks, team.
So like Nathan was saying, we were very hesitant to actually start simulating, and especially once we implemented any of those software debugging, we basically just kind of ignored simulating more. So another challenge we faced, like probably a lot of teams, is synchronizing each of the modules with itself and the hardware, which is causing our flickering screen. So we decided to propagate our TLAST and then eventually using the tagging system through each of the modules so we could make sure that each module is completed with whatever it needs to do for that frame. And then, yeah, we already discussed the draw arrays and then the colors being whack, which I'm sure also a lot of teams faced where we had colors outside of bounds and it was like overflowing or I guess underflowing. A lot of mistyping bugs like that would pass through synthesis and then we'd not understand why it's not working and we have to just look through a code and eventually find, oh, this is completely mistyped.
Yeah, do you think Sava would want to discuss the bug he found? This is one of the
Or are you talking
interesting
about the
ones.
double pop?
Yeah, it's related. It's a mistyping. It's just lazy autocomplete for me.
Yeah, sure. So we basically, I mean, I was looking through the code and I basically like figured out or like theorized that um the pop states were hitting themselves, were able to like, there was a way for the pop states to occur twice consecutively without us pushing. Because basically, popping, quote unquote, you're basically just copying from the register holding that like line start position. You're basically just copying it. You're not like removing the value. You're not doing anything else where it's gonna tell you if you happen to copy twice. So we ended up creating a couple of states for that to see when we were popping twice, and as it turns out, we were. So yeah.
And
Yeah.
those were mostly just error debug states. They don't actually, in a functional design, they actually don't need anything. But for us, it was actually quite helpful to debug.
Right. And then just real quickly, the results. So let's see a couple of things. So we didn't get our color wheel working, as many groups didn't. We also have. It seems that we miss about like maybe we're off by like a line of a pixel. If you look at the top right corner, sometimes we and it's not for every triangle we draw, but sometimes we're missing just a single strip. So I think it's something we still gotta work on. And then we also had some trouble. We can kind of form like the shape in the middle outlined by Voronoi, but it doesn't fully work yet. So
That's because we don't have the multiple draw arrays.
Yeah, I can't draw multiple primitives onto the or multiple.
Right.
Yeah.
So then there's just another cool application. It's just a triangle fan, which draws over itself many times, which I'm not exactly sure if that's undefined behavior, but I don't think so. It's definitely not undefined behavior for our design. But yeah.
I guess I'll take this one. Okay, never mind. You can just skip that slide. Basically, in the end, our result, like works quite functionally as like the rasterizer, like what we expected to do, especially with the inputs we give it from the driver. The issues we have with color wheel and Voronoi right now seem to be driver issues to fix in the future. But right now we have great synchronization of our frames. The triangles are accurate, and they interpolate and everything. And then we have a tougher system, of plumbing for debugging in the future. Although we'll have to do all that work for future modules as well if we want that. What didn't go as well is we started testing on hardware a little earlier instead of simulating. Not a ton of coordination, especially like even if you write down the whole approach, once you start like implement a lot of modules, like, I could feel people, might not have full sense of what's going on in a certain machine. So then not everyone can work on all the parts at once. So it kind of the load gets to distribute kind of weirdly. And then, yeah, we didn't finish some of our optimizations. So we had several, I guess, aggressive goals for performance and features, but and one of those would have fixed the slight line gaps that you find between strips and fans. But yeah.
All right, thanks, team. Interesting approach to, want to avoid simulation as much as possible, but I think you worked around that by having a lot of runtime debug as a possibility. And so I think it has to be one or the other, certainly. You wouldn't want to neither simulate nor have good debug information from a build. I think the main issue is more of the time associated with the build now, with the complexity of the design, that you want to try something, you want to do a new build. Well, you'll lose an hour, right? You're guaranteed, I think, to have an hour spent building, and that's if Vivado doesn't crash along the way. So but with your design, you had a lot of information you could gather from each build. So I think that's a reasonable trade-off. So thanks, team. All right, group 4, you are up.
All right, so these are kind of the roles we started with. I started working on primitive types for the most part, and then Dawson wrote most of triangle setup right off the bat. Aaron started on triangles reversal, and Jared started on traversal and test. Obviously, as we went, we sort of one of our components would break, so we would all converge on that component and work to fix the bugs that we were finding there. So while we started in individual components, we kind of all ended up in the same place at the end. And one thing that we thought was super useful is we have two voice channels in our Discord. So we're able to break up into two different groups and then just hop in and out really easily when we want to sort of ask questions. So that helped quite a bit with syncing up and working together. So the big driver change we made, which I think a lot of people ended up making, is we checked the status registers of all three of our main components to make sure that we were waiting to print to the screen until our render output and everything was actually done working. So in order to accomplish that, we obviously had to add the render status to that AXI light register for the render output, but that was pretty easy. We just propagated T-last all the way through. One thing that we thought was going to be a problem was with T-last, if we had multiple draw calls, which we never actually got working, but T-last would go high 3 or 4 times throughout one frame if we had multiple draw calls. So I think my group was talking to Professor Zambrino a little bit, and he suggested just waiting to make sure it was high 3 or 4 cycles in a row. And that's kind of a band-aid fix, but it seems to work pretty well.
It made sense to me. I think if we wanted to take the time and really like reason about what it means for it to be idle, because my concern was always these kind of in-between places where you go front to back and you actually miss it, or you go back to front and you miss it. So this is how I implemented it in my branch. I do it twice. So if I go back to front twice, I feel pretty good that it's actually idle, but that's not very rigorous either. So this is exactly not using a dual while loop, but yes, it's exactly how I basically implemented the same exact thing of checking it twice, and there should be some reason to believe that given the latency of doing that check, that if you're idle twice in a row, you're not in the middle of a draw. That was my thought process, and I'm guessing it worked pretty well for you in terms of glitchiness on the final screen.
Yeah, so we just still have a little bit of flickering on the final screen that we haven't had time to look into, but it helped. Like 95% of our flickering is gone with those changes. And yeah, as Ryan pointed out, we do have a nice do while loop in there. So this next component, I'll still keep talking because this is the one I did most of the work on, is our primitive types. Once we realized what it was actually supposed to do, this was a pretty simple state machine to implement. We basically took what we were given, and then if we were doing a fan or a strip, we would go to 3 different states here. So the read strip, we have a integer that just counts 0, 1, 2, 0, 1, 2. And depending on the value of that integer, we dictate which vertex register to write to. And then in this diagram, the fan reading logic doesn't quite work. There was a slight misinterpretation of what was supposed to happen there. And we actually only preserved one vertex and replaced the other 2 instead of preserving one vertex, shifting one vertex, and then moving a third one in. But for the most part, this is what our vertex and primitive types look like.
Am I taking this one? Because this one is also your primitives.
No, sure. I can take this one as well. You'll see our simulation infrastructure, we pretty much, simulation and testing for the most part, we would just kind of draw a triangle in Microsoft Paint and say, hey, it's supposed to look like this. And then we'd write a TCL script that would input the same points into our rasterizer. And then we would see, hey, does this look the same? And there's just an example of some of our waveforms. This is an output of primitive prim types for the strip. And you can just kind of see the 1, 2, 3, 4, 5, 6, 7, 8 vertexes propagating through there.
All right, so we had quite a few different challenges and bugs. A lot of them were Vivado, and then a lot of them were us. As you can see in the middle right image, it kind of destroyed AJ's computer by eating up all the RAM. And that was just one obstacle that we had to get around throughout this. And then another one was we realized in traversal, I believe it was, or test, I think it was, we weren't using the stack, similar to what somebody else was saying. So eventually, once we figured that out, we kind of started to move along a lot better. And on the right, I'm not exactly sure what that one is. I can't remember. I don't think I worked on that bug as much. But apparently it wasn't supposed to be a cache issue, and then it turned out that it possibly could be a cache issue. And then another thing, I just added the image a little bit ago. It looks like it's not on here for some reason though, is a we had problems with very skinny and obtuse triangles because what would happen, yeah, so like a triangle in the bottom right there, I don't know if it was just ours, but there were times when there was a line with no pixels on it, because if you look at the top right, there actually are gaps of island pixels apart from each other, and our traversal got stuck when that happened. But we ended up getting around that. Still, I guess not sure if we're supposed to have the island pixels. Ours do once it gets skinny enough, but our traversal can handle it now, so it no longer gets stuck on the skinny triangles.
And so like we can talk about the island pixel thing a little bit. For when we plugged, I can't remember what the specific values is, but we have a picture of it in our Discord channel. When we plugged these points into Reed's test, we found that Reed's test, when it draws the triangle, the pixels that it considers in the triangle are not necessarily what we thought. So we noticed that the 3 points that we actually gave it were not considered pixels as part of the triangle. And those are the 3 pixels, or the two corners, like the top right and bottom left corner would be on their own with nothing attached to it.
Yeah,
And
so
let me just interrupt there also that, Reed is not, paid to support this class. So, that code was using floating point logic, and we will definitely be running into that with these extreme edge case triangles.
Yeah.
Our math is okay, but our assumption of, 16 bits of precision for the fractional part, I did a lot of the paper and pencil on that for this setup to make sure that you would never underflow, but I can't actually guarantee that. So you may be able to build triangles that break this. So yes, that's a good job there. But I did not see, and I don't think other teams saw the island pixel. So I don't know the actual cause, or whether your team actually did it correctly, or there was still
Yeah,
actually.
we don't know, and we can show you more of it because we've got that all throughout our Discord. We were talking about it for quite a bit because we were really confused about whether or not the points that you give it should always be considered pixels that are in or not.
Well, it should be, but I do wonder. Well, there's a rounding issue though, ultimately, right? So you provided a viewport coordinate, and that could be the issue why we're seeing gaps between triangles. It's kind of the same effect. You provided viewport coordinates. That viewport coordinate is in the triangle. It certainly should give you fragment out valid for it. The math would be, area equals 0 or whatever. But then whether or not that actual location, when it gets rounded in render output, is actually moved 1 over to the right or 1 over up or down, that may result in an island in the final render, if that makes sense. But I also want to just mention briefly, I know it's tongue in cheek when you mention, not eating, sleeping, and things like that. And I think your team is there to support each other, but that is never my intention. So I would like everyone to eat, sleep, and breathe on a regular basis while working on these labs. And when that's not the case, I need to know. And
Part of it was our fault. We did start a little later than we would have liked.
Well, and I understand every team has to kind of gear up for it, so I get that too. But with 381, we have labs for 381, and I've done it enough times, and I've had different types of students work on those labs. I expect them to be challenging, but that people should be able to get them working with support and asking good questions. For these labs, I don't know. Okay, no one's done them before, so if it turns out it is a 300-hour lab, that's not my intention. But it's supposed to be hard. But so I want people to let me know that. I kind of got the idea of that, Monday night with how things were going. But it's hard to know with something like this exactly how many hours it takes. You are the beta testers for this entire class. So when you are finding that you are not sleeping or you're having nightmares about triangles, I guess I'm okay. If it's one nightmare about triangle, that's okay, I think. But if they're a recurring problem, we need to step back because it's okay. This is not supposed to be a death march of a class in which you all just kind of hate life in the department and Iowa State by the time you're done with it. So keep that in mind. MP-3 will stress different points, as I mentioned, and that's okay because it's a different kind of challenges I think associated with it. I think it's easier, but I don't know that. So we're going to find out. And that's just my final point about that. So I know you're joking when you mention that, but there's a real truth there, and I think every team was facing that.
All right. So we did end up getting results though, which ended up working. So that's pretty cool, you know. Our top left success took a long time of struggling on fixing the order of triangles, because what would happen is it would draw half of them, switch to the frame buffer, and then draw the other half, and we would have a flashing mess of triangles for every single frame. What we ended up doing to solve that is just check if we're done twice, and that made it really stable twice in a row. And so that advice was really good and helped a lot. For that middle one, in order to fix all the triangles, we would only draw 2 of them at once, and that would cause it to or the problem with it was that one of them was in such a position that the bottom row would just lock up, and so once we fixed it so that hold on, there's a lot of messages in chat. Okay, so once we fixed it so that the bottom row would draw and not lock up, the rest of the triangles just appeared, and so that was nice. Bottom left one, we had a huge amount of color problems, and so we edited the red triangle to show different colors at every single point, and so we would always use this one to kind of test, you know, is colors working. And there was many times where like we would have a different color calculation and it would actually just squish our triangle because we calculated a different value wrong because we were trying to fix colors. That was fun. The circle one, I think that's a picture of our triangle fans working. Our team just kind of got that working. And then the bottom right is us getting a stable triangle working. Yeah. This is a stabler version of our triangle strips. So before it would kind of produce about a third of the circle on one frame, then 2/3, then about a half, and then about a third, and then checking again twice if we're ready to go in the driver allowed it to draw mostly all of it, sans that little flashing part at the top left, which we haven't solved. But hey, it mostly works, so that's a success.
All right, thanks, team. I forgot we didn't really allocate time for Q&A. I think teams have been asking each other questions throughout, so you can always continue to use the chat for that. Even when you're done presenting, teams can feel free to ask questions about that. So I neglected to put that as part of the time we have today, but we're doing okay with time. We're going to get to, I think, Group 5 and Group 6, and that's likely it for today, and that's going to be okay. So Group 5, you're up.
I'm Isaac. I started with the triangle traversal and tried to support with debugging.
So another team member, Brian, he worked on the triangle setup and getting the debugging also.
And I'm Alexis, and I worked on the primitive assembly, mainly the triangle traversal debugging and some driver changes.
And then I am Parker. I worked on our test script, doing some of the driver changes. I worked on the triangle test hardware and also debugging. And for our status meetings, we synced up constantly on Discord, which was really nice. And then we did in-person meetings on Discord. So not in-person, but actual Discord meetings versus just using the text chat on the weekends.
Yeah, so here's our primitive assembly. As you can see on the bottom, like the bottom couple states, I added a strip state and a fan state. They're kind of states within the current state machine. And what I have it doing is basically it'll do the first triangle like normal, where it waits for the vertex 0, 1, and 2. And then if it's a strip, we will alternate between changing vertex 0, vertex 1, and vertex 2. And then a fan will alternate between changing vertex 1 and 2. If you draw this out, it does work because we don't really care what order it's in. the triangle setup will take care of it. So that's how I did the primitive assembly. And then I also waited for the T-last to switch between the primitive assemblies. And I believe I had the same issue as group 2 mentioned, where if you don't exactly know where the last signal goes, it can basically mess up the order of the vertices. So I made sure that we were only pulling last when it was a valid vertex, and then kind of saving that status when we went to write the triangle. Yes, this is the triangle traversal debugging. So the first picture you see is actually what we got originally, which, you know, isn't bad. It does look somewhat like a triangle. The reason why the whole middle is not there is we weren't waiting for that rasterizer status register in the driver. So that was a pretty easy fix. And it's kind of hard to see the second picture. It isn't solid. It's actually missing rows. So I went through a lot of debugging and watching how the state machine was going with the triangle traversal. And really the only state that was working like it should was the move right in. It was not ever moving left, and it was not doing the out states properly either. So in the end, what was happening is it would push down several rows instead of scanning the other direction. So I had to make a couple edge cases that when you push down, it starts scanning the other direction. And then once you do that, if you go to the next slide.
Yeah, so here we have the same triangle. We finally got it to fill in, but as you can see, it's really, it's not the full length that it needs to be, and it's not in the right area either. We went back through looking through our triangle setup, and we found that when we were calculating the area we were calculating was incorrect, which was causing the triangle to prematurely stop. And then we fixed that, and we finally had a full red triangle.
So Parker, calculate. Another group had I guess group 6 had the same issue with half a triangle because of half the area, but your slight miscalculation in the area also caused it to move over to the right.
I don't know if that was the exact cause.
Okay. That's impressive. I mean, you know, I guess we have to kind of work through the math and what it means to have the area be, you know, 1/2 plus 20% or something of what it's supposed to be, and then what that results in terms of a triangle. But this part, a couple teams did see half a triangle.
All right, this was a diagram that looks pretty clean, courtesy of Alexis on our big picture, and I think we've seen pretty similar stuff for a lot of groups.
So for simulation infrastructure, for the data that we use for testing, we captured data coming in from the ILA, especially for the original triangle, just to make sure we had the right format. Then I made a TCL script where I took a good chunk of time to figure out how TCL works, and I made processes for writing each of the different triangle types. So instead of having to go through and manually have a copy and paste setup for a triangle, as you can see in the lower left, I just say send triangle, and then I pass in the vertices to send. Same thing for the triangle strip and triangle fan. And those will automatically go to the next command whenever the state machine, the simulation is ready for the next command. When it came to actual debugging, we would look at the state and current positions being drawn. So on the right, the top image was kind of an example of what we would look for to know that we were even starting the right. We would go from waiting for setup in our triangle traversal to actually doing commands. We also found Reed's rasterizer calculator super helpful. And then the bottom right image is looking at an example of how we figured out that our moves were working properly. It's kind of hard to see in this example, but as more and more of the move right and move lefts go through, they get ever so slightly longer as we were going down and the triangle was getting wider.
So one thing that the area bug and what you'll see here is our color beam flip had in common was the in-wire math. Even though I had printed out the document and all of that, V2 and like in the in-wire 7 for, I think it was like C3 or something like that, It was we had V0 array instead of V2 array, and that took us, so all our math was wrong, and it took us many hours, and we had, and Professor Zambrino had to had to help us out with that one, because that was just a killer, where our colors were flipped and our area was wrong. Yeah.
And should we go back to the previous slide real quick, Dr. Zambrino? So lessons learned. We found that using certain values in our test script helped us find what was wrong. So first, it looked like our C5 was basically switched for two of the colors, but we had to change it, and we saw that it was actually just returning a negative number when it shouldn't have. So that was a good way to find it, and Dr. Zambrino helped us with that. The ILA was also very helpful in finding out the initial values for the simulation, what to put in that TIPL script. And patience and depth were definitely key, definitely with the triangle traversal. I probably stared at that for 2 hours, just figuring out why it was not ever moving left.
I mean, I can't agree more with that. You know, that last point there, Alexis, that it does require patience. It requires planning, and then the ability just to kind of stare at it, to know what you're looking for, and to have the patience to not just say pass or fail, move on, you know, restart it. And that I think is why your team, although you had a very fun bug, had, I think, significantly fewer bugs than other teams this week.
Cool. So this is our results page. The snowflake and the color wheel had a kind of special case that I'll talk about in a second. But as you can see, we had our triangles working. We had a very simple strip that we got working, and a fan where we did kind of a weird overlap case. And we were able to draw multiple triangles throughout all of our testing. When it came to the color wheel and the snowflake, the color wheel, we took out the inner triangle and the other draw call, so it's only the wheel. But for both of them, I actually made some custom, I modified the OpenGL applications to wait for a space press to swap the buffers. What this allowed us to do was figure out if any draw issues we were having were more timing related or hardware, like our logic related, because we were having trouble drawing those in the normal applications. And then Professor Zambrino has a story at some point, hopefully.
In the interest of time, though, not today. You know, Nathan asked the question that I asked your team this morning when I saw this slide. I would like us to get to the bottom of what is different in your primitive assembly, and it'd be nice, you know, this assignment is done. If teams are willing to just kind of just post, if they're not afraid of sharing with their classmates, your primitiveassembly.vhd. I believe, maybe someone correct me if they also had it perfect and I just missed it. I believe you're the only team who has that. I can't imagine it'd be traversal though. It has to be assembly. I don't know. I don't know why there'd be a one gap triangle missing. There's nothing that unique about that one triangle that the other teams were missing for that. So anyway, I don't know the answer for that. I'm curious, but that curious doesn't require you students to do anything for it. But I'd like to know what was different about your design than others that has that color wheel working as expected. We'll get to this at some point. We have time, but just barely for group 6. So thank you very much, group 5. So group 6, let's focus on what's a little bit different about your team's status, and then we'll call it a day today. Thanks, group 5.
Yeah, I'm Micah. My Josh and Raphael and Sam are all my teammates for group 6. There's a lot of stuff that that's in our slides that's really similar to the other projects that we've seen in previous groups. So we'll cover some of the big differences. The primitive assembly is one of them, I think. There are a few things that I changed that I didn't see in other groups. One of the biggest changes I made was like no more, like we took out the prim right stage. That just made our state machine simpler, I think, so that and it gave us room for 3 new states. These are the ones kind of on the bottom. Wait for vertex 0 again, wait for vertex 1 again, wait for vertex 2 again. These are meant to write triangles after we get the initial triangle. So yeah.
So here's triangle setup. I think for the most part, it's just same as everyone else's triangle setup. There's nothing special about that. There's just the end wires. What we did end up having were some small problems that ended up being triangle setup problems. So I think group 5 had the same problem where we were dividing the area by 2 because we kind of thought that that was correct, and then we realized we're getting half a triangle, and then Zambrino pointed out that we weren't supposed to be dividing it by 2, which made sense. So and then here's traversal.
Yeah, here's traversal. I mean, I mostly just did it in one go and somehow it kept working. So I just mainly focused on doing the driver for the rest of the lab and helping others debug their code. I also set up a test bench just to integrate traversal and triangle test by just using the right triangle vertices. And I think that's how we found out about the area divided by 2 issue.
So I did triangle test. It was pretty much the exact same as everybody else's. Yeah, a lot of it was done already. And then this is the big picture of the rasterizer. I'm not good at Draw.io, and it's pretty much the same as everybody else's big picture. Just stuff gets put into primitive assembly. And then Raphael or Micah, do you want to talk about these?
Sure. I mean, here's just some funny broken triangles. There's more in the next slides.
Yeah, we had a lot of broken triangles while we were debugging. We took the approach of implementing our hardware like often, but and that worked. We did manage to get some progress. We have triangles that are complete, triangle strips that are complete, as we'll show you later.
Oh yeah, here's the problem of calculating the area. So that was just multiplying it by 2 basically, grabbing or shifting it by 1 bit. So that was that problem. And then I think here's our last, actually, this is our last challenge slide. I don't know. So running RAND triangles was having this weird problem of like 3 of them showed up and then we would run it again and then all of them would show up, but it would like crash the FPGA. So we were trying to figure out what was causing that. We think like they were in a color buffer that was being like not swapped to or something like that. But yeah, that was a weird problem to show up. And I think Zambrino even tried to help on it and didn't understand what was entirely going on there.
Well, as I mentioned, debugging RAND triangles is pretty tricky, and it's an interface between your hardware and your driver. So if your rasterizer gets stuck like in a loop because it didn't push down ever and it just gets stuck going left to right or something like that for a weirdly shaped triangle, it's going to lock up that component. It depends on whether your driver checks that. And when you run the application again, maybe it works on the other frame buffer, but still getting locked up on the same triangle. So there's a weird interaction between when we're swapping buffers, which triangle we're failing on and what the screen looks like. I had a lot of teams, and I would still probably recommend this quite a bit, that if you're worried about, and it's mainly a triangle issue, but if you're worried about locking up, I was having teams, and I still recommend this, just reprogram the FPGA each time. It doesn't take that long if there's no Vivado memory leak. Reprogram the FPGA time, run that test. At least you have some confidence that what you're seeing on that test is related to that particular run. Oftentimes, I would have teams also power cycle the FPGA each time, because if you're not careful and maybe you weren't doing clear calls or something, you'd be seeing stale results, and that's pretty awful from a debugging test standpoint. Finally, share with the class your results.
Yeah,
team.
so here's what we ended up getting working. This was just last night. So that picture on the bottom left there, that's color wheel. That's about as good as we got it to look. It does move around and stuff, but obviously you can see there's some problems there. And I think there's some like splits between the triangles as well. That might be like a rounding problem. It looks like there's just some like clear pixels in between them.
You can see the bug though, right? I mean, this is supposed to be a little strip that's the
Yeah.
mini pointer, and you can see where it's going. Instead, you can actually see the connection. You must have decreased the number of triangles as well,
Yeah,
right?
we
Or-
did. That was just for
Okay.
initial testing, but I guess it's stuck in
But-
in our Git repository. So
Yeah, if you have time for one, I mean, you don't do it now, but one more test with the original number of points, and fixing the color overflow clamping issue, I think you have it otherwise, or it's extremely close.
Yeah, I think there's some other problems because this fan is supposed to look like that. We don't have a picture of what it is supposed to look like, but they should, instead of all being connected to that point at the top, they should all be connected to that point at the bottom. That's the top one. That's the fan test that we made, or Micah made. He made like a primitive playground, I think is what he called it. So it just tests like triangles, and then the strip, and then the fan, and then you can animate all of them as well. So that was handy in checking all the different prim types. And then the bottom right one, that's the triangle strip, which actually looks pretty good. But that's because it's a picture. It does flash sometimes, so that's another problem that we got to figure out. And some lessons learned: consider all the edge cases, don't touch things. Oh, the Vivado TCL scripts. We did make TCL scripts for primitive assembly, triangle setup, and then I think Raphael said he made one for the test and traversal, and then we made one for the
rasterizer.
yeah, and then we made one for the entire rasterizer, which ended up probably being the most useful one, because then we were able to simulate what happens when we send an entire triangle to the rasterizer, and then we can look at each component and what it does, and how it interacts with one another. So that was definitely handy in debugging.
another big lesson that we learned, I think, is from the other teams that are presented, is that there are other methods of debugging. We're definitely going to take a look at using those registers in future labs, because those seem like they were really helpful for debugging.
Thanks, team. And I know we're out of time. I know people have to drop out, and we will. And Team 7, I know we don't have time to go through yours. You had very nice diagrams, so I feel bad about this. Do you want to share this and talk about this briefly, or since I said we weren't going to get to you, but if you have time,
No,
if you're here,
sure.
you want to talk
Sure.
about your
Yeah, I'd be
real quick?
happy to. So we kind of recreated asteroids. So basically everything that you see on the screen right now is procedurally generated. So we made our own little asteroids using triangle fans. The ones on the board are actually just triangles, because we were worried we wouldn't get fans done in time, even though we ended up getting it done. So basically we made our own version of asteroids, where the goal is to just crash into as many as you can. And so it's a little bit different, but yeah. So, and it has like a full game loop. You can get to the end, you have a score. So if you go to the previous slide, it looks a little nicer because it's the actual OpenGL version on the board. So yeah, it doesn't look as flickery on the actual thing, and it has like a game over with the time and damage done. So, and yeah, we had a whole homemade physics system too. So everything on the screen is actually being simulated with collisions and mass and momentum and all that. So
I'm glad you got a brief chance to show that off. If you're willing, you should share that code with the class and let them see what you did for that. If you're happy to do that.
Okay, yeah, I'd do that.
Because I think it's pretty cool. So I'm sorry we didn't get to yours or Team 8, but I did review those, and I'll certainly be reviewing everyone's submissions probably over this weekend. Thanks for the demo day today. I think it was really cool. Let's regroup as a class. Let's collectively come up with a good plan for MP3 and the timing of it and the managing the stress and the workload of all classes, including this one. But I'm really excited to see an MP3 because I think with MP3, the implementations should look significantly different. So in MP2, you're following that structure. Everything looked kind of samey, and that was partially by design just to manage the complexity of it all. For MP3, I don't give you very much, and intentionally so. And I think you'll see lots of different approaches to solving, I think, some fun problems along the way for MP3. So let's leave things here for today. Thanks for the great demo day. Get some sleep, get some food, do what you need to do for yourself. Take care of yourself. I'll see some of you this evening. Otherwise, I'll see you in person next Wednesday. So Tuesday will be asynchronous. I'll post something and make sure we all get access to that content in time. Thanks, everyone, and see you next week.